All right, so today we are going to start our Unit 3, which is applications of differentiation. So we're going to apply using the derivative. And we are first going to start doing that by finding extrema on an interval. So 3.1 is our first lesson here. So our objective is students will be able to use their understanding of extrema to find the extrema on a closed interval. So let's go ahead and get started here. So in calculus, much effort is devoted to determining the behavior of a function f on an interval I. Does f have a maximum value on I? Does it have a minimum value? Where is the function increasing? Where is it decreasing? We will look at how derivatives can be used to answer all of these questions in the next few sections. We will then begin to apply these questions to real-life applications. All right, so that's kind of what we're going to be doing. So here is our first definition. So the maximum and minimum values of a function on an interval are the extreme values, or our extrema. Note that a function does not have to have a min or a max on an interval. So like in this image A, f is continuous on our closed interval -1 to 2, so it has a minimum here at 0, 1 and a maximum here at 2, 5. For part B, f is continuous on the open interval -1 to 2, but it has a minimum at 0, 1, but it does not have a maximum at 2, 5 because it's not a closed interval here. So this value is not included, so it's not a maximum. So for C, G is not continuous on the closed interval -1 to 2 because this point right here at 0, 1 is an open circle. It's hard to tell, but it is. So extrema can occur at interior points or endpoints of an interval. Extrema that occur at the endpoints are called endpoint extrema. So endpoint extrema. So we have this still as a maximum here for us. And that is not a minimum because it's not included. So no minimum there. All right, so we have the extreme value theorem. So that states if f is continuous on a closed interval, AB, then f has both a minimum and a maximum value on the interval. So note this theorem simply states these values exist, but do not tell how to find them. Okay, another definition here and an example. So definition. Points that may not be the highest or the lowest points on the graph, but are the highest or lowest points in their immediate vicinity are the relative extrema. Okay, so basically the absolute extrema, I'm going to write this off over here, absolute extrema are the highest and lowest points, and the relative extrema are the ones where it changes from increasing to decreasing. Okay, so that's those. So we want to identify the absolute and relative extrema of this graph here. So the absolute let's do max first. The absolute max of this function, so absolute means it's either the highest or lowest, so and we're looking for the max, so that's going to be our highest point. So our max here is D, so the point D is our absolute max, and our absolute min is going to be the lowest point. So the lowest point of the graph is, well, it's E, so that's our min, absolute min. Let's change our color. So then our relative max is where it's changing from increasing to decreasing. So, or vice versa. It can also go from decreasing to increasing. So we have B, right? So increasing here. So this point is where it changes. So we have B. And we want max, remember. So max is going to be where it's changing from increasing to decreasing, because that's where it starts decreasing. And then back to increasing, and here at D, it changes from increasing to decreasing. So those are our relative max. And then we have relative min, and relative min is now where it's going to go from decreasing to increasing. So that's here at C. A is not a relative min because it's not changing from increasing or to decreasing or anything. So A is just an endpoint for this function here. So you can have points be a absolute max and a relative max, or vice versa, an absolute min and a relative min. It just depends on what's happening in the graph. Like this case, we had the fact that we had the absolute max of D, and then we had a relative max D also. So you can have, they can be the same. So let's go ahead and look at our next example. So now we want to find the value of the derivative at each of the relative extrema. So we have this function here, f of x equals 9 times x squared minus 3 all over x cubed. And we want to find the derivative at this relative maximum here. So let's first find our derivative. So we got to use the quotient rule. So we have x cubed times 18x minus 9 times x squared minus 3 times 3x squared all over x cubed squared, which will get us down to 9 times 9 minus x squared all over x to the 4th. I skipped some steps of simplifying just for video purposes and being able to have room. So this is our derivative here. This is f prime of x. So now we want to find the value of the derivative at the point 3, 2. So to do that, we plug in the x value, which is 3. So 9 times 9 minus 3 squared all over 3 to the 4th. So 9 minus 9 is 0. So 9 times 0 over 3 to the 4th, it just ends up being 0. So the derivative is at 3 is equal to 0. Okay, so moving on. We now have example number 3. So we want to find the value of the derivative at each of the relative extrema shown. So we have a relative minimum here, and we want to try to find the derivative of this absolute value function. So at x equals 0, the derivative of f of x equals the absolute value of x. It doesn't exist because 1, it's a cusp and we know that it's not going to exist, but 2, if I take the limit as x goes to 0 from the left, and I find that function, we get the limit as x approaches 0 from the left of the absolute value of x over x, which is equal to -1. And then we do the same thing using our limit definition of the derivative, f of x minus f of 0 again, where x minus 0 then we get the limit as x approaches 0 from the right. And we get the same thing, the absolute value of x over x, but when we're plugging it in from the right, we get a positive one. And since our limits aren't the same here, since they're not equal, the limit, the derivative itself, it doesn't exist. So f prime of x is d and e, does not exist. Okay, number 4, example 4. So find the value of derivative that each is a relative extrema shown here. So now we have f of x equals sine x. So the first thing we need to do is find the derivative. So the derivative of sine x is cosine x. And we want to find the derivative at each of these points. So at this relative max and at this relative min. So when you want to find the derivative at these points, you just plug them in. So f prime of pi over 2 is cosine of pi over 2, which is just 0. So that's that value. And the derivative of 3 pi over 2 is equal to cosine of 3 pi over 2, which is also equal to 0. So at these points, the derivatives are 0. Which you can kind of tell based on what we know about graphing derivatives. Okay, so note at the relative extrema, the derivative is either 0 or it does not exist. The x values at these special points are called critical numbers. Okay, so critical numbers. So definition, let the f be defined at c. If f prime of c is equal to 0, or if f is not differentiable at c, then c is a critical number. Okay, so f prime of c doesn't exist here because there's a cusp, and the derivative is not going to exist at a cusp. And since this is the derivative is equal to 0, then we know that there's this horizontal tangent there. Okay, so example 5. We have this function, x cubed minus x squared minus x plus 2, and we want to find the derivative of it and find its critical numbers. So the first thing is we need to find the derivative. So just use the sum and difference rule. So 3x squared minus 2x minus 1. Constant is 0, so we can just leave it like that. So when we're finding the critical numbers are where either it doesn't exist or where it's equal to 0. By it, I mean the derivative. So we want to take the derivative and set it equal to 0 and find those critical numbers. So take f prime of x, set it equal to 0, and then solve for the critical numbers. So basically we're factoring this right now. So we get 3x plus 1 times x minus 1 is equal to 0. And then this, find both of these. You want to set them both equal to 0 and solve. So you should have x equals negative 1/3 and x equals positive 1. So this is where the critical numbers will be at for this given function. Okay, so just some guidelines here for finding extrema on a closed interval. So first, find the critical numbers f in AB. Evaluate f at each critical number in AB in the open interval, right? Okay. Evaluate f at each endpoint in the closed interval AB. And then the least of these numbers is the minimum and the greatest is the maximum. So make sure you write down these guidelines. Okay, so let's do an example, number 6. So find the extrema of f of x equals 3x to the fourth minus 4x cubed on the closed interval -1, 2. So the first thing we want to do is differentiate. So let's find the derivative of this. So 3 times 4, 12 to the third minus 12 to the second. Okay, so now we want to find the critical numbers. So to find the critical numbers, set it equal to 0. Okay, we can factor out a 12x squared. So we have x minus 1 equals 0. So we either get, so 12x squared equals 0, or x minus 1 equals 0. So x is equal to 1, or x is equal to 0. So these are our critical numbers. So since f prime of x is defined for all x, these are the only two critical numbers. So these are our critical numbers here, 0 and positive 1. So now what we want to do is take the values that we just found, the critical numbers and the interval that we're on, and find the maximum and the minimum value. So basically we're going to plug each of these numbers, 0, 1, -1, and 2, into our function and find the maximum and minimum. So we'll start with f of 2. So 3 times 2 to the fourth minus 4 times 2 to the third. So all that ends up being 16. And then let's do -1, which is 3 times -1 to the fourth minus 4 to the -1 to the third, and that ends up being 7. And then f of 0, the easy one, is just 0. And f of, what am I missing? 1. So f of 1 is just -1, because 3 minus 4. So, okay, so since our lowest value here is -1 out of these 4 values, this here is going to be our minimum. And our highest value of these 4 values is 16, so this is our maximum. So that's what it said in our guidelines, that the lowest value is the minimum and the highest value is the maximum. Okay, let's move on to number 7, and let's find the extrema of f of x equals x squared minus 3x to the 2/3 on the closed interval -1, 3. So first start with your derivative. So we get 2 minus 3 times 2/3 is 6/3, so 2x to the -1/3. Okay, so we can write f prime of x equals 2 minus 2 over x to the 1/3. And we want to find the critical numbers for this. So we need to set it equal to 0. So 2 minus 2 over x to the 1/3. So we can do common denominator, so 2x to the 1/3 minus 2 all over x to the 1/3, which then is 0 equals, let's factor out a 2, x to the 1/3 minus 1 all over x to the 1/3, which then is, let's see, we can, let's multiply by x to the 1/3, x to the 1/3. And these cancel out, and that's just 0. So 0 equals 2x to the 1/3 minus 1. Divide by 2. Those cancel out. So now we're over here. 0. We still get 0. So x to the 1/3 minus 1. Add 1, so 1 is equal to x to the 1/3. Well, cube it. So x is equal to 1. Okay, and another thing that we want to make sure that we look at is the fact that we can't have this here be 0, right? So this can't equal 0. So that is also going to be another critical point. So we're going to want to plug that into x to help us find our max and our min values as well. So let's go ahead and do that. So since we have f prime, it does not exist. So that's that. And then we want f of 1. So if I plug in 1, I get 2 minus 3, which is negative 1. If I plug in negative 1, I get negative 2 okay, so I get negative 5. Sorry, mental math. F of 3, because that's our interval here, is approximately negative 0.24. And then we have f of 0 because it doesn't exist. So we have to use that as a critical point. So f of 0 is just 0. So with doing this work, our lowest value is 5, negative 5 here. So here is our minimum. And our highest point, these are all negative, so this is the biggest one, so maximum here. So there's your max. Okay, so we have one more problem, but we are actually going to look at this one in class tomorrow. So we will do this one first thing tomorrow because it's a lengthier one with all of the trig functions in here. So tomorrow let's look at this first example and find the relative, or not the relative, but we'll find the extrema on 0, 2 pi. So we'll do that one in class tomorrow. All right.